Hi, it's Phil from My Math Teacher is Terrible. Thanks for joining. As the title suggests, we are going to talk about a geometry problem today. Specifically, we're going to talk about a geometric proof, and I think my intention in this video is to sort of improvise a little bit, but really not talk about like the specific proof of this problem, but rather use this problem as a vehicle to discuss how I go about doing a geometric proof, and maybe you can observe some things that I do and maybe pick up some tips. I don't feel like I'm going to write out the proof in words or in the formal, 2 columns and all of that sort of stuff, but who knows, maybe I actually will. So yeah, this is from a high school geometry class or a middle school geometry class. I got this, I was working with one of my favorite students. You know who you are, and you also know this question. The both of us sat down and were working on it just during a normal tutoring session, and it was really a bit of a head scratcher. The wording you'll see in a second, for me, seemed like it's almost like improbable, if not impossible, but obviously not impossible, but seemed really interesting. And it's something that I actually never heard before, mostly because I really didn't consider it before. Okay, so what the heck is this problem? All right, I wrote it down as best I can in my handwriting, and let's talk about it. Okay, so the problem is, given a quadrilateral, and they really mean any quadrilateral, given a quadrilateral, prove that connecting the midpoints of consecutive sides yields a parallelogram. Always is really what they mean. And twice now I've said is really what they mean, and that's a key proof-related practice, is to see, we really have to pick apart the words, right? Writing a proof is very specific. The order is more or less specific, and then the wording of the statement and the reason in the 2-column format is also pretty specific. So maybe let's go through it and just talk about what they're asking for by looking at the words that they are using. Okay? I'm going to underline them in red as we go, and then we'll talk about them. Okay, so given a quadrilateral, right? That seems pretty specific. What the heck is that? We'll remind ourselves. Prove that connecting the midpoints of consecutive sides, right? So 1, 2, 3 bits straight away, yields a parallelogram. 4 bits. Always. Okay. But the key thing, so first we've got to orient ourselves to the problem. They mention a quadrilateral, they mention midpoints, they mention consecutive sides, and then they mention a parallelogram. Not too bad. Can we remind ourselves what these things mean? Certainly, right? Let's maybe number these. Here's number 1, number 2, number 3. That's how numbers work. 4. Okay. Yeah, let's talk about number 1, a quadrilateral, right? Quadrilateral. Quad is in there, right? Quadrilateral. Lateral. Right? Quadrilateral is a 4-sided figure. Now, just as a simple reminder, and I think you cover this early in geometry in terms of dealing with shapes, we're talking about what they call convex shapes. A hexagon is a convex shape. It has 6 sides. A rectangle is a convex shape with 4 sides. This is not a convex shape with 4 sides. This is a concave shape. And why? Because there's a little cave that you can hang out in if a bear is chasing you, right? Or a honey badger. All right, so this is a concave figure. We're not talking about these guys. In fact, I'm going to erase it. But that's how I remember what a concave figure is. Maybe you will too. Okay, so it's a 4-sided figure and it's convex. That's a quadrilateral. That's number 1. Great. 2. Midpoints. Not too bad, right? I have a line. And I have capital M, here's A, B, and this is equal to this, right? That's the definition of midpoint of a line, right? So maybe we're going to use that somehow. 3 consecutive sides. Okay, so let's draw a quadrilateral. Consecutive sides. 1, 2, 3, 4. Sometimes called adjacent sides. Right? Certainly in triangles we use adjacent when we're talking about trigonometry and things like that. But they're basically any two are adjacent. Any two are consecutive, right? 1 and 2 are consecutive sides. 3 and 4 are consecutive sides. 4 and 3 are consecutive sides, right? As you walk around the figure, either clockwise or counterclockwise, they're the two sides in a row. That's what consecutive means. Right? This side comes after this, just like consecutive numbers. 1 and 2 and 3, they're consecutive because they come after, one comes after the previous. All right, so still not so bad. I don't think any of these are bad. Number 4, parallelogram. Long word, right? But what is it? Parallelogram. What are the essential defining characteristics of a parallelogram, right? It's a quadrilateral, right? It has, let's put A, has opposite sides are equal, right? Opposite sides are congruent. Man, that's terrible handwriting. Congruent, Phil. Opposite sides are parallel. Right? This is just talking about the sides. Well, I'm going to rewrite this. You don't deserve that. You deserve a lot better, don't you? All right, congruent. Not much better, but definitely a little bit better. These are about the sides, but a lot of times they have things about the angles as well, right? So something about the angles. Opposite angles. Congruent. So opposite sides are congruent and parallel. Opposite angles are congruent. There's another one, D, consecutive angles are supplementary. Consecutive angles are supplementary. Sum equals 180 degrees. Right? The sum of the angles is 180. That's what supplementary means. What else do I know about parallelograms? I know some stuff about the diagonals. Right? The diagonals bisect each other. That one I'm going to leave out. Okay, not so bad. So we actually have a bunch of ideas about, and this is a bunch of words about what a parallelogram is about. Sometimes, and geometry is definitely one of the visual practices of math, let's talk about what parallelograms look like. All right, what's a parallelogram? What's a parallelogram? What's a parallelogram? What's a terribly drawn parallelogram? All right, and then another one. Talk about the names and whatever of these things. I'll make some marks. Blah blah blah. What do I use? Black probably. Okay, right. We have names for these guys. We know this is approximately a square. I mean it to be a square. This is a rectangle. This is a parallelogram. That's a general parallelogram. This is a rhombus. Right? All of these are related in a way. Right? Certainly we know. Let's start with a square because that's the most specific. All the sides are congruent. And it's not possible to move any of these angles to make these sides not congruent. So they're all congruent sides with at least one right angle. But if at least one of those angles is right, then all of them has to be right. Also, these sides are parallel, right? And I know that. Okay, now let's take a moment to refresh our memories about parallel lines and what is a super useful diagram. I'll draw it below here, I guess. Everybody in geometry should know this diagram. All right? Here's L1, L2, and T. Right. Two parallel lines cut by a transversal, right? So now I'm fleshing out a little bit about what it means to be parallel before I discuss this a little bit. Now I'm going to mention something that a lot of math teachers don't mention. In this diagram, there are only two possible angle measures. That is all. If I cover up this line down here, I certainly know that whenever two lines cross, I have what they call vertical angles, right? Those are equal, and then these guys are also, oh my gosh. These guys are also equal. Right? I know that that's true all the time. But if these lines are parallel, I know a bunch of stuff about the angles over here. So I can just start with that. And now when these lines are parallel, I know a bunch of stuff. I know that alternate interior angles are the same, which means this. Then I could stop because now I have vertical angles again, right? And that's it. There are 8 angles here, but only 2 angle measures. That's all. That's the beauty of this diagram and how amazing it is in Euclidean geometry. Right? When I'm given this, by the way, this diagram or use of this diagram is on every SAT exam. So pay some attention to it and get it in your mind because this is super useful. Okay, back to this thing, right? So now, if I think of this guy, how would I do this? I don't want to get this too crazy, but if I think of this line here as a transversal, cutting this line and this line, and these same side interior angles, which we know, by the way, same side interior angles in this diagram, they add up to 180. They're supplementary. Right? And these are consecutive angles, it turns out. Just the way adjacent or consecutive sides, these are consecutive angles. As I walk around this square, I have this angle and this angle. Consecutive angles are supplementary. They add up to 180. But if one of them is 90 degrees, the other one has to be 90 degrees. That's what I mentioned by the at least one of them, but if one of them, then all of them. Okay, if I think of this as a transversal and I have 2 consecutive interior angles, right? That's these guys. They add up to 180. But what else does it tell me? It tells me that these lines are parallel. Okay, now I have a pair of opposite sides parallel. I have opposite sides congruent for sure. This is a square because it's very specific. And now if I flip the square around, I get the same figure, right? That's the square has what they call rotational symmetry. Right? I can turn it around 90 degrees and I get the square again, which means these sides are also parallel. I guess I'm supposed to use 2 of those. I don't really know. But that's it. Done. This is a parallelogram. Opposite sides equal and parallel. Opposite sides equal and parallel. And then actually opposite angles are congruent, right? These guys have to be 90 as well. And then consecutive angles are supplementary. Bam, there it is, right? And all of these can be done similarly. In a rectangle, we know it's the same situation. Opposite sides are equal and parallel. Opposite sides are equal and parallel. Done. That's all we need to know to show that we have a parallelogram. And then if I take this and I change one of the angles, any one of the angles, to something other than 90 degrees, for this guy I get this, and for this guy I get this. But it's just called any old general parallelogram. This one's called a rhombus because I have equal sides. Right? That's a special. This is just like a square is a rectangle with equal sides. A A rhombus is like the general parallelogram with equal signs. Okay, so what this really is asking or saying is I have a four-sided figure, and actually the choices for the four-sided figure are these four choices. That's it. A rectangle, a square, a rhombus, or the general parallelogram. All right, and this is the general one because all these can be, if I take this and tilt them up so I have one right angle, I have this. If I squeeze it together so that this side and this side are equal, I have this. If I squeeze it together so that this side and this side are equal to this side, and I have a 90-degree angle, I have this. So everybody here is a special case of this guy. So what I want to do is, I probably want to generalize as much as I can, and this is the guy. This is the general one. I want to stay away from these two especially because they're so common that I feel like my eye would like trick me because they're already suggesting that I'm going to get a parallelogram. And I'm just like, oh man, if I see a square, I'm done. But am I really? I'm not sure. Right? So I want to be as general as possible. But that really is it. So I've actually picked out these four things, discussed some sort of general parallelogram situation, also thought about how to show that lines are parallel by using my friend here. This is like such a cool diagram and is amazing. Like it helps in so many ways. All right, so now I feel like I've talked about all the four key things, but I somehow have to like jumble all of this stuff up into something that's concise in two columns that shows the situation. One other thing I just want to talk about briefly is sometimes we also want to talk about the diagonals of a parallelogram. Well, the diagonals of anything. I mean, I can draw a diagonal in here, but that's a square. Sometimes I want to talk about this and see if that has any sort of bearing on the situation. But that's really it, right? Given a four-sided figure, convex, right? Not the cave where you can hang out. Midpoints of the sides. Consecutive sides. So connecting midpoints of consecutive sides yields a parallelogram, always. Right? That's it. So I know that these sorts of things, I got to chuck them in there, mix them up, and see what happens. Okay, so now I actually have never tried this move on camera before, so we'll see if this works well. I have this crazy cool whiteboard that I can do this with, and hopefully we don't knock down some stuff. Pretty nice. Makes a convincing sort of click, like I know what I'm doing. All right, so let's have a look at that. All right, so we talked about what I'm expecting to see. How do I come up with some sort of diagram now? Again, being the visual practice, how do I come up with some sort of diagram that will help me here? And again, it's super easy to draw a classic, right? Let's say that's a square and connect its midpoints, and you probably have seen these types of diagrams before, right? And suggest, yeah, that looks sort of blah, blah, blah. I know, but this is like such a run-of-the-mill quadrilateral on the outside. But this is the kind of thing we're talking about. Let's just talk about the square for a second. I did all the midpoints of the sides. I connected them, and they're telling me that the thing that's formed inside is a parallelogram. And it looks like a square again, right? Turns out it is a square again. But like, this is too specific, I think. I really want to think very generally and then see if I can actually show it in the specific cases. A proof that says given any parallelogram. So I want to think really generally. This kind of thinking, it's okay. We could do it with a rectangle. We could do it with a run-of-the-mill parallelogram. But students who work with me see that a lot of times I draw what I consider to be, I don't want to say extreme, but I think I'll say extreme or maybe like a non-mainstream sort of figure. Right? I want to draw something that exaggerates some of the relationships, and then in this case, exaggerates a general quadrilateral that we start with. Right? We're talking about the quadrilateral that we start with. So let's do something like this. I don't know. Something like this with a really small side and then two sort of long-ish sides, but maybe not. I want to avoid something like an isosceles trapezoid. That's easy to recognize. Maybe I want to put a right angle in there. Let's redo this. Let's try it again. I want to do something real weird. Right? Let's do something with a right angle. So let's do this, and then a small side. Right? And I'll just, for laughs, I'll put the right angle in there because I mean it to be that. I feel like this is extreme. I can't say that any of the sides are equal. It's sort of a cut-off right triangle, which I guess is run-of-the-mill. But when I did this, I felt like, okay, so now I have a really general-looking thing on my hand. Okay, so now let's commence with what the instructions are. Finding the midpoints of all the sides. Now I'll be approximate here. I'll be approximate here. I already don't like that these are like almost, I mean, I guess any 2 points here will be collinear, but it looks sort of neat to me, and I'm maybe not happy with that. Okay, and I'll do the midpoint here. And now I'll connect the midpoints. And sorry if I block this, I just really want to get this right. All right, this is going to be hard. Not bad. Not bad. Okay, not too bad. Notice I oriented the figure sort of weird in space, right? I didn't put it with the base like horizontal, or even if this is sort of a cut-off right triangle, but I actually didn't draw it in a right triangle like configuration like I normally, like you may see in a book, where the base is like parallel with the piece of paper, blah blah blah. Okay, so this is a pretty general case. Now, is this true? It appears to be true, right? I mean, this, well, let me get two markers and let's have a look at them. Let's have a look at them in an interesting way. All right, these two markers, they appear to be parallel. And then again, they appear to be parallel. It's crazy, right? These are four non-equal sides, and they appear to be opposite sides equal and parallel when you draw the thing with the midpoints. Super interesting. I mean, when I drew this diagram with my student, and then I drew 3 or 4 other ones at some other point, trying to come up with crazy looking ideas about like what this thing could be about. It's super interesting to me. Yeah, okay, so what now? Well, it appears to be true for this randomish thing that I drew. And there's nothing about these sides, like even this, like these sides maybe appear to be parallel, but I could see a situation where I just move one of them and it's fine. Because if I move this way, it's going to change where the midpoint is here, and it's actually going to readjust itself. It's actually true that this happens in all random quadrilaterals. Super interesting. Okay, but how the heck do I find any information about this? This line here, let's start here. How do I know that this is equal to this? How do I even go about doing that? That's pretty weird. And then, all right, so suppose magically that I found out they were equal. How do I find out that they are they're parallel? Well, I'd have to use this as a transversal. What else can I use? I don't think anything, right? Because the sides of the figure in black actually don't cut across a pair of parallel lines, do they? No. So it seems like pretty difficult. And I took this and I spun it around, and then I drew some rectangles and some squares and some general parallelograms. I was like, man, what do I do here? And for whatever reason, it took me a while to think about what's up with the diagonals. Let's see if I can reproduce this so we can talk about the diagonals. Okay, so I have this guy. Is that about right? Yeah, it seems about right. This is a right angle here. Maybe it's down further than this. Well, whatever, as long as it's approximately the same. I really am interested in the diagonals. So let's draw a diagonal and see if I can succeed at that. I'm going to stand in front of this to get it right. Not too bad. Okay, so now I have this diagonal, and now in blue, I'm actually going to draw these guys. And what the heck happens? I'm going to do the midpoints again. Sorry that I'm standing in front. Okay, so the midpoints are on here. All right, this is basically the same. I know that like these are a little longer, but it's the same sort of like, in my mind, an extreme sort of shape. Now, I could have done this and connected these guys, but I'm actually not interested in that. I did it anyway in the original. I drew both diagonals and the quadrilateral inside it, but let's do this. And stop. Okay. Now, if I get rid of this, and maybe I think I actually will get rid of it, because now I want to talk about just this part of the diagram. Actually, I'm not going to get rid of it because I need it. But let's disregard this part of the diagram. So what do I have? I actually have a triangle here, right? This triangle with a red base and the two black sides, right? And triangles are the basic two-dimensional closed figure, right? The first one has three sides. Everybody else has more sides, but the most basic, and all areas and things like that can be computed using just triangles. They're awesome. But what do I know about triangles in a line like this? Let's maybe draw it in an orientation that we've seen before. What do I know about that? This doesn't necessarily have to be a right angle. What do I know about that? These are the midpoints of both of consecutive sides, right? These are the midpoints of consecutive sides if I go this way, right? They are. They have a special name for this guy, right? Midsegment. What are the properties of the midsegment of a triangle? And this is the breakthrough part. If you can already start thinking ahead to see where I'm going, great. But this was the breakthrough part. After I did this and drew the diagram a couple different ways, this was the breakthrough. Because it's like, of course I know something about this. What are the things that I know about this? I know that if this side is called B, I know, let's draw it in other colors because we're going to draw some information about it, write some information about it. If I know that the base is called B, I know that this guy is called 1/2 B, the midsegment, right? Its length is half the base. I know that. Does that help me here? Don't know yet. All right, but the other thing that I know is that the midsegment of a triangle is parallel to the side that it doesn't cut. So I know that this is parallel to this. All right? Those are the two most important things. I know some stuff about the perimeter. I know some stuff about, like, the perimeter of the top triangle is half the perimeter of the outside triangle. I know a bunch of those things. But I'm not sure how those were to help me at that point, right? But man, what did I just show? I showed that this side is parallel to the diagonal. That is awesome. And this is worth committing to in green because it's the yes. Let's do that. Let's see if I can do this without ruining my diagram. Cool. What else do I need? Well, I need to show that's this guy, right? This guy and the diagonal of the outer quadrilateral are parallel because this is the midsegment of this triangle here. Now, what else do I need to show? Yeah, I need to show this. I'm going to step in front and draw this so I get it right. I need to show that this line and this line are parallel. And we're already eyeballing it, right? We're already seeing that they look sort of parallel, especially with the suggestion made by this less than perfectly straight, but enough to get the impression. How the heck are we going to do that? Well, I'm actually going to cover up this part of the diagram. and see that I have a triangle again. And I have a triangle again where I connected the midpoints of two consecutive sides of the triangle with a red base. So here's one triangle, and here's the other triangle, right? And what do I know about the midsegment of this? This is a midsegment. And what do I know about it? I certainly know, where's my green? I certainly know that this is the case. Right? And now this diagram is really, really, really banging home that 1, 2, 3, those lines are all parallel. Now, the red diagonal was not in the problem and not in the problem statement. In fact, this problem didn't even have a diagram supplied. So I actually came up with some sort of example and then started breaking it down. And certainly diagonals are something to explore in geometric figures, certainly. But right away, I'm like, how the heck am I going to prove? And then with this sort of like insight, boom, I actually have a pair of parallel sides. How am I going to write that in the proof? If L1 is parallel to D, right, the diagonal, L1 is parallel to D, and L2 is parallel to D, right, this is L2, is parallel to D, then L1 is parallel to L2 by transitive property of being parallel. Right? That's some proof language right there. Right? We transit through the middle one to show that these guys are parallel. And really, that's kind of the end of figuring out what the heck is going on here. Because as soon as I draw, I'm going to draw my midpoints of my consecutive side, or all the sides, all the given sides. Right, there they are. And now I'm going to take this diagram and I'm going to generalize it. I'm going to get this out of here to make, because this actually doesn't really help us that much in the diagram. I thought it would be interesting. All right, here I am in front again, but I'm going to do something different. I'm going to draw the other diagonal. And now I'm going to draw in blue the other sides. All right, I have this pair. I have this pair already drawn in this diagram. What about this pair? Less than straight. But I can go straight to the result using the basis. I can say this guy's parallel. Well, I'm going to use the two arrowheads here. It's parallel to this. Because this is a midsegment of this triangle here with the red base. And yeah, this is parallel also to the red base because it's the midsegment of this weird looking triangle here. Again, extreme shapes, right? This is an elongated, crazy looking triangle. But it actually is crazy enough or not too crazy to show that we can make this connection just like we did here. And again, through the transitive property of being parallel, if this is parallel to this and this is parallel to that, these blue guys are both parallel. Done. That's cool, all right? So now I established that opposite sides of this guy, right? And now I'm going to draw it onto this diagram because I established that these guys are indeed parallel to each other. Right? So I have a pair of opposite sides that are parallel from this diagram, and then a pair of opposite sides that are parallel from this diagram. So I've actually shown the first key quality of what they're asking us to do. Right? I'm connecting these. It's showing that the sides are parallel, and that the opposite sides are parallel. It's showing that. Okay, now I have to show that the lengths of I think I only have to show the lengths of one pair of opposite sides are the same, or that they're congruent. Pair of opposite sides is congruent. Let's go back to this diagram. So I'll choose the one with the one arrowhead on it. Let's go back to that. So I did establish that. They're parallel. But then I also see they have the same base, which is the red. And what do I know? I know that any midsegment with this base if its length b, is also 1/2 b. So on this side, I have that this guy is 1/2 b, if this is the red is the base. And then when I cover this side up, I know that this is exactly 1/2 b as well. I mean, now the proof is going super fast, right? I immediately know that this is the case. And I'm going to do this in green also because now I have this side and this side equal to each other. I can do a similar thing with this side and this side, right? Because these are mid-segments of a triangle with the red base, and it's half of that number, so it's definitely the same length. So I can give them 2 strokes here in green. And now we'll merge these into our diagram. I've got these guys. I'm drawing these down here so they don't get squished here. That's one disadvantage of drawing an extreme thing, but it means that this whole line has 2 strokes like this guy does. And similarly, over here I have 1 stroke and 1 stroke. And what did I just show by doing this exercise? By the way, I drew only one like little extra thing. This little extra thing like unlocked the whole problem. Right? I showed that any quadrilateral, the black, when I connect the midpoints of consecutive sides, it produces a parallelogram. Opposite sides parallel and equal, opposite sides parallel and equal. I'm done. I'm absolutely done. That's it. And for any crazy looking quadrilateral that you can come up with, it's the exact same proof. I feel like in my mind, using the side lengths is a little more intuitive than using the angles, but there's certainly a second way that you could do it, or there's probably a mixed bag way that you can do it. But again, my goal here is to just discuss how I go about doing a proof. Let's go back to the first slide with the first board full of information and just look and see that we actually show that kind of thing, right? Given a quadrilateral, any quadrilateral, I just drew a goofy one that was a little extreme looking. Prove that connecting the midpoints of consecutive sides yields a parallelogram, always. And remember I said squares and rectangles, they're pretty facile in terms of like showing this kind of thing, and our eyes can be a little fooled by how common these are. But as soon as we pick something that's a little weird, I mean, even these are run-of-the-mill. Certainly, it seems that we were able to talk about the first principles, draw an interesting diagram, and then a generalized diagram, and then show, now we can draw like an isosceles trapezoid and see that that's the case. I mean, let's draw a little one. What should I do here? I'm going to leave this in case anybody's writing it down or whatever. I'm going to get rid of this guy, though. Let's try an isosceles trapezoid. Let's just try it and then eyeball it and see if it appears to be true. I'm going to get in front here, draw the midpoints. The midpoints here are super easy, but super wrong, it looks like. I don't know, I'll make them a little bigger. That's a good. Yeah, and then here also super easy, right? Because this has to be, the line between this has to be parallel to both bases. And then this has to cut the thing in half. It more or less does, but let's see what happens when I connect. I mean, is that crazy? It appears that's the case. Please forgive my imperfections. I can see that this triangle and this triangle are not exactly the same. They should be. But again, just eyeballing it and going, dang, can I come up with a quadrilateral where this is not true? Now, turns out that that's not a proof. Is exhaustively trying to find every quadrilateral, that's not a proof. But if I were to like label this properly, like, quadrilateral A, B, C, D with diagonal BD and AC, and then inscribed maybe parallelogram, DRUM or something, or well, actually I can't use D again. Maybe A prime, B prime, C prime, D prime. I don't know. Whatever. we can come up with a solution. And the other thing is the importance of a diagram and marking up the diagram. I marked it up, I marked it up, I marked it up. And I talked about it and then applied it. Marking up the diagram, I can't say enough about that. If they supply a diagram, the first thing you should do is mark it up as you read the problem. Excuse me. And then basically we're going to look at our diagram or our sequence of diagrams or whatever we talked about, and we're going to take all that stuff and mix it into a proof in a logical sort of way, right? We're going to say that ABCD is a quadrilateral, given, blah, 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 like that sort of thing. Construct the midsegment of triangle ABD. And then we'll say that whatever is parallel to BD, definition of midsegment, right? That sort of thing. And that's how I go about doing these sorts of things. Again, I'm improvising a little bit here. I did consider this problem and solve it, but it took a while, and I really had to call on a lot of like different things. The thing that I'm glad that I tried this out because that led to this. And once I knew this, boom, the whole thing was unlocked. And I do say that to students from time to time about geometry problems, like one angle and the whole thing unlocks, or one side and the whole thing unlocks, or one arc of the circle and boom, we can figure out this sort of thing. It appears to be true, especially in these like problems that are constructed for your high school classes. All right, so that's about all I want to say about this particular problem, and just kind of some of my general comments about how to really think about doing geometric proofs. A lot of it is this. The writing, I feel like, for me, is the minor part. Getting the notation correct, of course, is super important. But how do I actually play around with something to figure out how I'm going to write the proof? This is like a classic sort of way that I've been doing these things forever. And how did I get good at it? Like I tell most of my students, start with 25 problems in a particular type, then go to 50, and then you'll probably be doing just fine. But I mean, for simpler problems, I've done hundreds and hundreds and hundreds of them by now. Because you'll see later on in your math career, stuff like this mixes with calculus, mixes in your engineering classes. And they all all the disciplines come together to form a solution to a very interesting problem, no matter what that might be. All right, well, I just want to thank you all for joining me. I also want to thank whoever came up with this problem for coming up with it, because I really had a good time dealing with it, and also had a good time discussing it for you guys. Just let me know if there's anything else I can do. If you got a problem that you'd like me to work on or discuss, I'm super happy to do that. I love getting submissions from my students and from people that I don't know. If you're on the other side of the globe, that would be awesome. But if you're right here in my backyard, that's cool too. Not actually in my backyard. Yeah, so thanks for joining, and hopefully you learned something. Leave a comment, subscribe to my channel, I'd love that. And again, yeah, thanks for showing up. I really appreciate that. All right, well, I'll see you next time. Thanks.